Starting. And we are live, it looks like. Hello, AST111X. Yeah, now we're live. Hello, AST111X. My name's Frank.
My name's Bill.
And we're going to chat for about an hour on some of the questions that you asked and present some other stuff associated with solar systems. So I'm Frank, and I'm the crazy guy in the videos and on the discussion boards. So I'm the instructor of the course, and research-wise, I do stars in general. I particularly like stars that go boom, and all the associated things that go around with stars going boom. So that's kind of what I do for research.
All right, and I'm Bill again. I'm a researcher at ASU, and I'm also, you'll see me in the discussion boards answering some questions from time to time. And I also study stars. I look at interesting class of stars called white dwarf, which are more or less the size of Earth, but the mass of the sun. And they're sort of done doing burning, but they still are interesting. They can also go boom. So that's why I came here to work with Frank.
Little booms and big booms, depending on what kind of boom you want to do. So yeah. So feel free to ask as we go here. Looks like we have on the order of about 50 viewers at the moment. So if you have any questions as we go along, feel free to pop them into the discussion board topic and we'll try and pick them up. So the first thing we're going to do in this session is go through some of the questions that have already been asked. We'll answer some verbally. Some of them we may follow up on with prose if we don't get to them, or we want to add some depth to the reading. So, Bill, why don't you pick one and start one of the questions that have been asked?
Yeah, I'll start down there. One of the fourth or fifth questions there from, let's see, Renisha03 asks, when the Earth goes through precession, will its tilt, 23.5 degrees, always stay constant, even in the future over time? So, very closely, yes. It stays at 23.5. It just happens to rotate through a circle and stays very near 23.5 degrees. If you wanted to be a little more precise, there's actually this interesting phenomenon called, we were looking this up just minutes ago, the Milankovitch cycles, which actually, because there's more than just the Earth and the Moon affecting Earth's precession, you actually get tugs from, say, Jupiter and Saturn, these other larger bodies, and they actually cause the Earth's tilt to wobble a little bit, come almost between, say, 22.5 and 24.5, somewhere in that region. You could there's a good Wikipedia page that explains all that Milankovitch cycles. I'm sure if you guess the spelling, you can probably get pretty close. But to the 0th order, yeah, it's pretty much constant at 23.5 degrees throughout evolution.
Yeah.
I get that right?
Yeah, absolutely. I was just going to say something, and I momentarily spaced it out what I was going to say about that. But yeah, no, that's great. Okay, as long as we're in Renishaw's 03's questions, I'll pick up the one right above it where Renishaw 03, and I hope I'm saying that right, asks, if the Greeks were not able to detect parallax at first and had to believe the Earth was centered, how did they suddenly get the ability to detect parallax? So Aristarchus used the heliocentric model to prove that the sun was centered, but how did that help detect parallax? Okay, several questions in there. So let's go over what the Greeks actually did do and why they came to the conclusion they did. So the Greeks believed that all the stars were on the celestial sphere, sticky dots on that translucent sphere. So all the stars are at the same distance. So they actually considered a model where the Earth orbited the sun. That was a definite possibility. And they reasoned that if the Earth orbited the sun, then at different times of year, you would be closer to some parts of the celestial sphere than you would other times of the year. And therefore, you should be able to measure or see an angular difference, an angular separation between those two times in the stars. This is parallax. Okay, so they recognize that if the Earth was going around the sun, you should be able to see parallax. But they could find no parallax. Well below their technical thresholds. And so they concluded that either one of two things was true. Either the Earth orbits the sun, but the stars are so far away that you cannot detect parallax with the naked eye. And number two, there is no parallax because the Earth is at the center and the sun goes around the Earth. And they rejected the first part, the first answer, that the stars, because they couldn't imagine that the stars were actually that far away. that was more ludicrous to them, that the stars would be at that kind of a distance. And therefore, the Earth not orbiting the sun was their conclusion. It was not an upfront assumption about their cosmology. They put their cosmology to the test, didn't detect the parallax, and so concluded that the Earth was at the center. Humanity's hunt for parallax. And so just to follow up on Renishaw's question, so the Greeks did not detect parallax, nor did they the domination of the Earth orbiting the sun. That model didn't come until about the years 1500 or so. That's a topic of this week's material, actually, with Nicholas Copernicus and company. And so once that model was set, thus began the hunt for parallax, because it had to be there. The stars had to be really far away for the parallax to be that small. The first parallax from a star was actually measured by Bessel in about 1850 or so, if I remember correctly. And yes, that Bessel. And so a very readable story about humanity's hunt for putting the third dimension on the space, which is what parallax is. That's told in a book that goes by the title Parallax, The Race to Measure the Cosmos, and that's Alan Hirschfeld is the author of that book. And it's a great story about the hunt and the technology needed to measure parallax. And so at the end of the day, the stars really are that far away to make the parallax that small.
Sometimes it's just the frustrating answer.
Yeah. Yep. All right.
All right. How about I take another one here? Another one from Renishaw 03. Do solar and lunar eclipses occur for other planets in our solar system? Okay, if I want to be difficult, our moon doesn't do anything really interesting. I guess maybe there could be a transit of our moon and from the perspective of other planets, but probably more what you're thinking is, do moons from other planets cause solar eclipses to occur for someone that would be on their surface, or lunar eclipses? And the answer in some ways is yes. I think technically for something to be an eclipse, it needs to be fully covered. So for example, on Mars has two tiny moons that are really more like captured asteroids, Phobos and Deimos. And they're actually much closer to the surface of Mars than our moon is to our surface. But because they're so small, their angular size is very, very tiny. And they're actually not a very impressive sight in the sky and could not block out the sun. So they would merely transit it, and there would be no lunar effect. They're too small. They would just go through and shadow, and you wouldn't get any spectacular lighting effects. But if you go out to the gas giants, where you actually do have some large moons, I actually don't know which ones you might have eclipses for, but it'd actually be an interesting, you have the tools to do this exercise. Go through, calculate out the distances from the surface of a planet to the moon, see what its angular size is, compare it to the angular size of the sun from that planet. Yep. And if the moon would appear larger, then you should be able to see eclipses.
Yep.
You want to say something, Frank? Or?
Nope, that's exactly right. Yep. You've got all the tools you need to do that. So let's see, if I had to guess.
I would guess Io causes eclipses if it crosses the right plane. Like for some viewers on the surface of Jupiter, if there was such a thing, I would think Io would be able to block out the sun, but I really don't know. That's just kind of some intuition.
Yeah, I think you basically need a big moon.
Yeah.
You're going to need a big moon to block out the sun, and that moon the bigness gets smaller as you get farther away from the solar system, because then the sun gets smaller. So, but yeah, it's actually an interesting question to look at. But yeah, there's no reason for eclipses not to happen on other planets.
Good exercise.
Large enough moons. Good exercise. Ooh, I smell a new lab question being generated.
I'll remember that for next time I'm taking it.
Another application of circles and radii and angles. Let's see. W. Rodriguez R. Asks, in the lecture, we clearly see the zodiac consists of 13 constellations. However, only 12 of them are popularly known. What is the reason that Ophiuchus is unknown to most people? Bottom line is because when they made the zodiac, they just ignored it. 12 was a great number. 12 was a holy number. 12 was a magic number. It's why we have 12 hours of daylight, 12 hours of sunlight. It's why we have 12 months of the year. It's why there are 360 degrees in a circle, because it's easily dividable by 12. You know, this number 12 comes up over and over and over again, because that was the magic number back in the Babylonian times, when the zodiac was made. So the Babylonians certainly knew that there were 13, that the ecliptic went through 13 constellations, but that was an inconvenient fact. So they just ignored it to get the 12, and now the world is right because there was the magic 12 again. But there are in fact 13. And if you look at a constellation map in the ecliptic, you will see that the constellation Orion is actually very, very close to the ecliptic. And because of some of the effects Bill was talking about earlier, where you go through precession and other effects like that, the boundary of Orion in about 1,000, 2,000 years will sneak up into the ecliptic, I do believe. I haven't done that calculation, but that looks about right. Which means in about 1,000, 2,000 years, there will actually be 14 constellations in the zodiac. So that's that story. All right, next.
Okay, I'll take a little less technical question from Astro Enthusiast 04.
Ooh,
great name.
Yeah.
What are your advice for a high school student who is going to take astronomy as a profession in the future? Okay, so I'm still, as far as astronomers are concerned, relatively young, and still getting into the game.
Oh, so am I. So am I.
Yeah, well, we're all.
Oh, absolutely.
We're all young here.
But we're all young.
So I just finished graduate school about a year ago, and so I'm still pretty early on in my career. And I think for astronomy, it's difficult, I think, to do a career in astronomy with only an undergraduate degree. I don't know of a whole lot of ways that happens. Maybe you can work for a museum, or maybe go into education, I guess, if you're okay with being flexible and doing some sort of science education. But if you really want to be an astronomer and be, doing simulations or taking data from telescopes or designing new instruments that are going to go into a new NASA mission, you really do kind of have to go through 4 years of school. And I would recommend taking things that are beyond what are required. Really need to dig in deep for a lot of math, a lot of computer science, really double down on computer science. I think sometimes the curricula haven't caught up, but that's really everything now. And I did my background in physics. We didn't have an astronomy major, and that also had the advantage of being versatile. But if you're really doubling down in astronomy, you could just do an astronomy major, but really get a lot of math and computer science, and then try and get into a research program and get a graduate degree that can set you up. But I would say you really need to be confident that you want to do it. The nice thing for astronomy right now is if later on you realize, okay, this particular field isn't for me, or it's too hard, the skills you gain studying math, physics, computer science, astronomy, it's all problem solving and critical thinking. And there are a lot of people looking for the skills that we happen to have. We don't think it's necessarily, right now the big relief valve, if you're an astronomer and you want to get out, is to go into data science, which is this growing field. And
particularly in finance.
Yes, finance would love to take some more astronomers, because we're good at dealing with vast sums of data and at building models. So you isolate something down to a very simple version of itself, extract as much value out of that as you can, and then add one layer of complexity. That's a very useful skill. A lot of people get overwhelmed with details, and astronomers are trained to discard spurious details. And so even if you don't end up in astronomy, it's not like you're going to be you're gonna become an astrologer and work on the street corner and
Yes.
tarot cards. So there are ways out, but I would caution against thinking that you could be an astronomer and do something that you would think of as an astronomer with just a 4-year degree. You really have to go all in, and you're probably not going to be getting a real job until you're in your late 20s or 30s. So it's a lot of work. I really enjoy it so far. I haven't been turned off yet. I'm still here, but it's not for the faint of heart. Frank, do you have any thoughts?
Yeah, several thoughts there. Yeah, by number, astronomers are about 1 in a million.
Ooh,
relative to population. So in the U.S., it's even a little smaller. It's 1 in 10 million. So it's a rare breed, and as Bill mentioned, it takes some time. It takes some dedication to get a real job, quote unquote. So one thing I would advise when you're an undergraduate is try to get into a research program while you're still an undergraduate. Typically, if you're a junior or senior, you want to try and hook up with somebody who's doing a research program that you're interested in. So whether it's theory, observation, or instrument building, and get involved in research early. This will give you a leg up getting into grad school where you will do more research. So I would do that. The other thing that you mentioned, Bill, which caught my ear, was the ability to simplify things down to the essence. And this is exactly why we are doing order of magnitude estimates, so that you learn that skill. It's a valuable, valuable skill in any field, to be able to estimate quickly and easily a quantity of interest that comes up. Until the day where, and I'm not even sure I want to be there, when they wire Google into your brain directly, it's a good thing to be able to think creatively on your feet and come up with the essence of a problem relatively quickly. So,
yeah, I definitely agree with that.
Let's see, I will take Jason Weathers' question. I'm probably going to punt part of this to you, Bill. Arecibo Observatory, Puerto Rico's giant radio. The telescope does not look like it can track objects like arrays can. That's true. If I have a stationary laser pointed at the heavens, twirling like the Earth would do, wouldn't I get to a distance where it appears to cut through space faster than the speed of light? Are the SETI folks mad? I don't know how they can collect enough data at length for any given star system. Okay, there's a lot of questions in there. So let me take part of it. So it's absolutely true that radio telescopes such as Arecibo are fixed in the ground. There are other ones like that. Currently, the world's largest radio telescope is in China. Like Arecibo, it's built between Para valleys. So yeah, you can't steer the telescope, and what you rely on is the Earth rotating. And then, of course, as the Earth goes through the seasons, as we go through that 23.5 degree tilt, you get to see 23.5 degrees of the sky. So Arecibo, over the course of years, can map out a band on the sky, not insubstantial band across the sky. So it is true that any given object you're looking at sort of goes across your field of view according to how the Earth rotates. So any given time that the object of interest is in your beam is relatively small, but you get to watch it the next night, and the next night, and the next night. And so you can watch the same object over and over every night as it passes across your field of view. And then year after year, as you come back to that object in Earth seasons. There are lots of telescopes besides Arecibo that look at a fixed patch of the sky. For example, the Kepler telescope, which looks for exoplanets around other stars, only looks at one part of the sky. It just stares in one direction. And there's lots of advantages to doing that, because you can look at the same objects over and over and over again. And if you're looking for little tiny things that are circling the stars, like planets, exoplanets, that's an advantage to be able to stare for a really long time. In other words, get a really long integration time. You can add up all those observations at once. So that's how fixed field of view telescopes, whether it's Arecibo or others, work their magic on taking observations. Did you want to say anything about?
Yeah, I can talk about
or faster than light.
Yeah, our thought experiment here. So the idea is if you you're on Earth, which is rotating once a day, and you shoot a laser out into the sky, wouldn't it seem like at far enough distances, this laser's moving around at the rotation speed of Earth, but now you've got it at a large distance, that it would be moving faster than light. And in fact, no, this would not happen. Sorry. But this comes, I think, from the idea, like thinking of light as a rigid rod or something like that, which that's a separate question I could talk about another time. But light is probably best thought of as being a series of packets of light going out, these photons. And once it's been emitted in a direction, it's just going to keep going in that direction. So even if the thing that emitted it starts rotating around, we're moving around this way, the thing that was emitted here, when I'm pointing this direction, keeps going that direction even as this moves. So we're not going to see the stream of light moving at a speed faster than light. You're actually going to see almost, if you were looking from above and you were able to see the photons coming up at you, that's kind of hard to think about, but you would probably see more of a spiral as Earth is going around as the light comes around. Then when you come around a full day later, you would see the next sort of arm of the spiral going around and around. Now, if you asked about having a giant, astronomical unit long steel bar that you could magically hold up,
whoa,
you're going to have some other interesting problems. It's probably going to get ripped out of your hand from centrifugal forces, but thought questions. Then you'd have to start worrying about special relativity. Things would never go faster than the speed of light. You would actually end up dealing with some other more exotic physics before you would get that far.
Yeah, that if your final ending point is things going faster than the speed of light, you've ended up in a bad spot. It doesn't work that way. So are those SETI folks mad? No, because it doesn't happen. Either that or some giant worldwide conspiracy that, all those SETI folks are hiding this fact from the rest of the world and have been for 20 years. But we're here on this podcast or video cast to let you know in on the secret. It's all superluminal. No, it doesn't happen. Sorry. Okay. Next. Let's see what else we got here. Speaking, we were just talking about the Kepler satellite and how it looks for exoplanets. So L. Hodgkins writes, is the newfound Kepler planet going to be looked for oncoming life, perhaps? Absolutely. The Are We Alone driver is huge. It's a fundamental driver for a lot of things we do, right? Are we the only ones in this universe or not? That's why we go to Mars, and why we look for stuff. So these days, finding another exoplanet is not that exciting. We have about 2,000, 3,000, 4,000 of them. So adding one more, garden variety, one more is not that exciting. And so where the state of the field is right now is not necessarily finding more exoplanets, but characterizing the atmospheres of the planets that we do have, right? So you're looking in particular for things like biosignatures. You're looking for things that, at least as far as we know, only have a biological origin. So
it's probably worth mentioning that these are so far away, like we aren't getting a snapshot of a planet. When you see a picture of a planet in a news story, that's an artist's rendition.
Oh yeah.
They're, so distant. I think a lot of people I talk to end up thinking like, oh, we're just taking pictures of planets. No. So instead we find evidence of a planet. Maybe we see that it passes in front of the star and the star becomes dim for a short period of time in a repeatable way that we understand, or we can, there's a number of ways that we can detect these, but you're almost never doing direct imaging. So
right.
Very clever techniques they're using to characterize the atmospheres is something you can't even really
see
of in the way you would normally think.
Yeah, exactly. Thank you for making that clarification. You don't actually see these things. They're too small. They're too dim. But nevertheless, you can detect them. And where the game is these days is to characterize their outer layers looking for that life. So to answer the question, I would say I don't know about that particular one. I don't know which one You don't mention the telephone number of that particular one, but almost certainly, particularly things that are deemed to be in the habitable zone, so where water is in a liquid form, the temperature is right for water to be in liquid form, those will certainly get a lot of attention. Anything that is Earth-like in the habitable zone will get extra attention. So, yeah.
All right, I can take a question from Corn98. Hello, so my question is, if another solar system with roughly the same number of planets passes through our own solar system, what would happen? What would that do to the various orbits here? And what would happen when the two stars pass close to one another? Thank you for the answers you might have. So the first thing I should mention is, like, because there's so much space in the solar system, probably nothing would collide, but it would still be extremely calamitous, almost entirely just because the other star, or even if a very large planet passed through.
Super planet crash.
Yes, you should check. You should Google Super Planet Crash or Super Planet Crasher, a fun video game of trying to make something be stable that should not be stable. Basically, build a solar system and see how many planets you can shove in there before it becomes unstable and the orbits decay and hit each other. Very fun, very frustrating. You can waste a lot of time on it. Right. So as another star moves through, it's going to very dramatically alter the orbits, especially because you're adding a new source of gravitational energy that is moving in time relative to everything. So not only would it screw with all the planets' orbits, but it would even move the sun out. Maybe it would start kicking us. It wouldn't kick us out of the galaxy, but it would kick us into a very strange orbit within the galaxy probably as well, or at least within the local region. So yeah, that would be very, very bad. That would be the end of it.
Very bad.
Probably it may not fully disrupt the solar system, but it would make it very chaotic for a very, very long time until it could settle down.
Yep. Not a good thing to happen. Let's see. Christoph Schock asks, I was wondering why the orbits of the planets of our solar systems are almost like a plane disk, like the rings of Saturn. Could it be possible there's a solar system out there with planets that have orbits like the small objects in the Oort cloud, for example? Okay, so this is actually two-part things here. So I'll answer that. So the formation of our solar system is actually a topic we cover in week 4 in some detail. So I'm going to punt a little bit on that first part of that question and wait till week 4. But the planets orbit in a plane because they came from a disk, very thin disk, as it spreads out. So that's why we have the ecliptic. That's why all the planets are in a plane, because they basically came from the disk material that formed the sun. And again, I'm going to punt a little more detail on that until week 4. Is it possible that other solar systems have Oort-like clouds? Yes. Whether they would have Jupiters out in their Oort cloud or planet 9s out in their Oort cloud, okay, there's a relevant topic, is a TBD. I'd be surprised if there was Jupiters, gas giants, but whether there's a planet 9 super Earths out there in the Oort cloud floating around, it's quite possible. In fact, we're looking for one right now in our solar system. That's what planet 9 is all about. And I have another question, another thought regarding this question. Man-made satellites and space debris are orbiting the Earth all around. It's like a sphere, so to speak. Yes. What would happen to the sphere over a long period of time? I think you have two effects. One, a lot of those things are not orbiting all that high. They're still within the atmosphere of the Earth, that exosphere of the Earth. So the gas density is low, but it's not zero. And that causes atmospheric drag. And so I would imagine that all the low stuff is going to have atmospheric drag, which will pull it back to the oceans or maybe the land. So they're going to crash back into the Earth. The other one is a dynamical friction. So basically a bunch of bodies interacting with one another creates sort of a drag on all of them. And so then the other possibility is that on long enough time scales, if they don't fly in, that all the satellites would form into a disk of material, because disks are a very natural phenomenon. That's why we see, that's why our solar system came from a disk. That's why we see the rings of Saturn are in a disk. So I would say one of two things: either they're going to crash into the Earth, atmospheric drag, or they're going to form into a disk from dynamical friction. That would be my guess. Oh, and just a point there. You know, when they show those, pictures of the Earth and they show the satellites around them, okay, the size of the pixel in that image is far, far, far larger than the actual object. So it makes it look like, you know, we've blotted out the sky from all the things up there. Okay, well, that's not true, right? You can go outside and look at the sky and go, okay. But is there a lot of stuff up there? Yeah, absolutely. So it becomes more and more of a concern. But I'm just urging some caution when you see those pictures of man-made satellites completely covering Earth's sky. That interpret that carefully. Those pixels are far bigger than the actual objects.
And is there now actually a requirement for new things going up that they have to have a plan for decommissioning it?
Yeah.
Like I know some of the first ones they're just floating up there, but you eventually
all kinds of junk up there, right? From rocket stages and stuff that broke off, and yeah, there's just. So I think NORAD, North American something, they're responsible for tracking all that stuff above some size limit, and I forget what that size limit, but I remember it struck me as somewhat small, like tens of centimeters and up is what they track, because of course a 10-centimeter object moving at a relative speed, several thousand kilometers per second or per hour, is going to cause some serious damage to your thing. So it's kind of like the asteroid belt, right? The asteroid belt is somewhat the same thing, right? In movies and in pictures of asteroid belts, it's always this hugely dangerous place, right? Or, you know, you go through it and, you know, your odds of getting whacked by an asteroid are huge. That's fiction. There's a lot of space between asteroids, which isn't to say you shouldn't take care or you shouldn't fly above it or below it to avoid it. But, you know, this hugely crowded space where you're going to get whacked.
It's not the Star Wars asteroid field.
Right. There we go. Okay. Anything else?
One more.
There's one more. Awesome.
Yeah, they got Euro 117 here. Says hello and thank you for hosting the live session, Dr. Timmies. I don't think you have mentioned this in any of your lectures, but I was just curious to know, why is it that the motion of our planets goes from eastward to westward direction versus the other way around, or in any case up and down around the sun? Does that also happen in other solar systems that have been discovered? Thank you for your attention. I'll let you take this.
Oh, thank you. Okay. There's a couple of things in there. Okay, so basically, you know, as we talked in the lectures and we talked a little bit on the discussion board, there was a couple of threads related to retrograde motion, that during its normal motion, the planets drift about 1 degree per day relative to the background sky. And this is just because the Earth is going around the sun. The Earth is not stationary, the Earth moves. And so that has an impact on when you see Mars rise, for example, in the background. I think the east-west is not versus west-east. I have to think about that, but I think that's just the relative direction of rotation and how we define east and west. So if we had defined east and west the same way, but we were, instead of rotating counterclockwise as viewed from above the North Pole of the Earth, if we were rotating clockwise, that drift would be west to east. I think that is true. Of course, we'd probably flip the definitions of east and west if that was the case. So then we'd be back to where we were. So some of it is a question of how you define east and west and relative to your direction of rotation. I hope that answers the question. And then the up and down thing, yeah. So we covered this in one of the discussion boards, and I mentioned it in one of the videos, that as the sun goes around the center of the Milky Way, not only do we go around in orbit, but kind of like horses on a merry-go-round, we go up and down. We oscillate up and down as we go around. And the reason we oscillate up and down is because the Milky Way, the disk of the Milky Way, has lots of stuff in it. It's got things like giant molecular clouds, which hold a lot of mass. That is most of the mass. We've got gas. We have a lot of material in the Milky Way forming a source of gravity that the sun responds to. And so that response to first order is to do a periodic motion up and down. And I will put that thread as a reply into this. The reason the planets don't do that is because we don't have a significant disk of material in our solar system. We had one, that's what created the planets. But then when the sun turned on, all that material got pushed out of the way. Topic we cover in week 4. And so it cleared out our planetary system, so there's no longer material there for the planets to interact with gravitationally and hence bob up and down to the extent that our sun does as it orbits the galaxy. Does this happen in other solar systems that have been discovered? Does it happen? Almost certainly. Have we detected it? Not to my knowledge. We're real satisfied just detecting exosolar planets these days. And next step is characterizing their atmospheres. Their motion around their galaxy is probably 1 or 2 steps down the line. So no, we haven't confirmed it with other galaxies, but we're not special in any sort of the way there. So I would certainly expect other solar systems orbiting their galaxies to behave in a similar manner, because gravity is gravity. Okay, is that it? Any more?
That's all the questions we have for now. I'll refresh and see if there's any new ones since we started.
Okay.
Oh, 2 minutes ago, Core 98. Is a lunar colony possible? And if so, why has no one attempted it yet?
Okay.
I would say yes, it's possible. And the reason why is that it would be prohibitively expensive to keep getting supplies up there.
There's no water.
Yeah, unless you wanted to be some military superpower and launch missiles from the moon, that's about the only practical thing. I guess the super billionaires of the world could vacation on some lunar colony, but
they talk about mining the moon on occasion, right? Like if the moon's going to be serious, valuable ores, right? There could be something to mine it.
Yeah, that's true.
I think now that you think about it, that was the wasn't that the opening of 2001: The Space Odyssey?
I actually have not seen it yet.
Right.
I'm a little behind.
Oh, okay.
I don't remember.
I think they're mining. Well, okay. Other than the ape thing, I think they're mining on. I believe it was the moon, and they uncover the monolith, and the monolith sends a signal, which then sets off the whole story. And the reason they're on the moon is because they're mining. So. Okay. But yeah, I think you're totally right. One, there has to be some driver to actually put a colony on the moon, given the expenses it's going to take to do it. Humans are so fragile. We don't do well in space all by ourselves. We need all kinds of things.
There isn't a source of oxygen available on the moon, is there?
Not to my knowledge. You probably have to break down the rocks in some chemical way to release oxygen to get that out.
You need to somehow get a source of oxygen and a source of water, and then maybe you could build up some sort of greenhouse thing, but otherwise it's going to require constant resupply missions, and getting to the moon is not cheap at all, let alone trying to bring in raw materials to build something. So, but yeah, it's possible. Just you'd need to be a crazy evil billionaire to make that work, I think. Or you would have to be evil.
Sign me up, Scotty. I'll do it. I just need $1 billion. Actually, I probably need a few billion.
Seeking some venture capital.
Yeah, okay. Good idea. Maybe I should start a Kickstarter campaign for this. Maybe I'll get $1 billion that way.
Good luck with that.
Promise people I'll make a lunar colony or a Mars colony, start competing with Elon.
If you back it, you get 50% off of your $1 billion ticket to get there.
Hey, I'll give you a free trip there. I'll give you a free trip if you invest well enough. So, okay, let's see. So we're out of questions. So I'm going to do a little thing, which I call Time Through the Ages. If you like, it's one of the video modules that didn't quite make it as a video module, so I'll do it for you live here. Let's see, how shall I do this? So I have to share my screen. Screen share. And I will do I will try just doing the PDF. Let's see. How does that work, Bill?
Can you full screen it?
Okay.
That's better, but
Now let me try full screen. Hold on. Full screen. Whoops, there it is. I had it. How's that?
that is black.
Black.
Oh, now it's you.
Me? Okay. Let's try something else. I'm going to change my screen share. So how do I stop my screen share? Okay, this is not good. Okay, I'm going to share my whole desktop. Start screen share. And now we go full screen. You should be seeing that wonderful infinite.
Yes, very trippy.
How about now?
Perfect.
Perfect. Okay, awesome. Okay, so there's a little thing called time. So Steinbeck only wrote one comedy, The Short Reign of Pippin IV. It's very short. It's a short story. Outside his usual fare of despair in California fields. So you should check it out. It's a nice little read. It's called The Short Reign of Pippin IV, and one of the quotes in there is, "The passions of astronomy are no less profound because they are not noisy." So this is a story about a commoner who happens to be, he's in France, he happens to be related to the king. For political purposes, he is made king of France. He doesn't like it at all. And so to escape, as shown in the book cover there, he dresses as a commoner, gets on his motorbike, goes out into the country and observes the stars, and hence where the quote comes from, that his passion for astronomy is just as profound as being king. A few weeks later, it's politically expedient for him not to be king, so he's not king anymore. So there's quite a bit of social and political commentary within Steinbeck's book. Check it out. It's a great little read about astronomy and other stuff. Okay. So this one's Time Through the Ages. So we're going to talk about time, and there's a nice little clock and the Big Dipper, and just a nice little piece of artwork there I happen to like. So 'tis the season. So when we start out, we are agriculturally dependent, and that means knowing when to plant. And it also means knowing when the first frost is, when to pick, etc. All great. Just do what the sun tells you to do, and all is good. Okay. But as societies grow more complex, they desire fixed dates for things like festivals, July 4th, pay your taxes, April 15th. They want fixed dates for things. And this is what introduces the difficulty of keeping two clocks synchronized. One is the seasonal clock. This is what the sun is telling you the season is. And your man-made clock, if you like, your calendar year. I want to impose a calendar on the celestial motions. And keeping those two synchronized is a battle we're going to cover over the next several thousand years and how people dealt with it. So there's the 4th of July in Tempe in 2007. That's an example of a fixed date. So what's a year? So for reference as we go along, the seasonal year is defined as vernal equinox to vernal equinox, that's spring equinox to spring equinox. And it is about 365 days, 5 hours, 48 minutes, 46 seconds, or 365.2422 days. And that, of course, is the Persistence of Memory by Salvador Dali on melting clocks and how you get clocks to stay synchronized. So the yearly calendars were often based originally on the summer solstice to summer solstice. That's a natural point. Or when a first star happens to rise with the sun, and this is known as the heliacal rising. And so the Egyptians, who of course were a dominant power in their time, used Sirius, the brightest star in the sky. By the way, Sirius is a double star system. It has a white dwarf in it, those things that Bill studies. And so the Egyptians used Sirius. It was the brightest star in the sky. And it rose early in July when the Nile was in flood. And with an economy based on the Nile floods, the heliacal rising of Sirius was the most important day of the year. Time to pick, time to go. And so that became their first day of the year. That was their January 1st. Their January 1st was actually in July when Sirius first rose. The image there shows the Canis Major and the constellation Sirius, and it is just rising above the horizon before the sun. This is the heliacal rising. Sirius rising just before the sun does. And I actually did this for Alexandria, Virginia in the year 2000 BC. So it's close. Canis Major. So that's where Sirius is. And because it's in the Canis Major, Sirius is sometimes known as the dog star. And it's from the Egyptians' use of the heliacal rising of Sirius in early July. That's where we get the phrase, dog days of summer. Because the dog is rising with the sun, dog days of summer, and on it goes. So a lot of our phrases are old. They come from astronomy. So you have a year, and a year is kind of a long time. And so what's a month? So how do you mark time intervals within a year? And the first marker used was the moon, and that is the root word of month. So month, moon, something if you like. And there are two main obstacles with using the moon to subdivide the year. The image here is the Aztec calendar stone. Mexico City, and the Aztecs used the moon. They had a lunar-based calendar to keep time within a year. The first obstacle to overcome is that the lunar month is not constant. It varies. It varies between about 29 and 30 days. And this variance is due to using something called the synodic period rather than the sidereal period. And we're going to talk a little bit about that because it'll come up a couple times. It will be useful to bring this up a couple times in the course. So the synodic period is easily observable, okay, but it's not very useful. The synodic period is the time between identical sun, earth, and some object alignment. So take the moon, for example. So if I go from full moon to full moon, quarter moon to quarter moon, new moon to new moon, okay? Those are identical alignments. That's easily observable. The moon is full or it's not, but the time period between those full moon to full moons varies a little bit. It's not a constant time period. On the other hand, you have something called the sidereal period, which is the time between the same Earth, star, and object alignment. So you pick a background star and you wait until your object of interest, the moon, for example, aligns with that star, and that is the real period. That's the period that you're going to put in Kepler's third law, that you're going to put in Newton's variation of the third law, but it's harder to observe. It's not so easy. So you have the synodic period, which is easy, not so useful. Sidereal, that's the real one. And the way I remember that is the sidereal, that's real. It's got the word real right in it. So you know which one is the right one, or the one you would use in actual formulas to calculate something. So let's go through why those are different. Okay, so here I have the sun, I have the earth, I have the moon, and I have a background star, and I'm going to start my clock when everybody's aligned. Okay, so everybody's all in a line here, and I'm going to let the clock go. Okay, so what does the earth do? The earth goes around in its orbit. Okay, the earth and the moon go around in their orbit around the sun, and when you come up with the same earth, that's the blue dot, purple, the moon, and the distant star alignment, this is the sidereal period. This is the real period. It is 27.322 days. But the moon is not full. Why? Because it's not opposite the sun. So you have to wait a little bit more time for the moon to travel a little bit extra distance to get back into the full moon position. And because the Earth's orbit is not exactly circular, it's a little bit elliptical, as we will discover this week, the time to reach that point of new moon is variable, 29 to 30 days. So we have the synodic period and the sidereal period. The second obstacle that a calendar has to overcome is that even if you decided you're going to use the average sidereal lunar month, which is about 29.5 days, that doesn't fit into a seasonal year of 365.2422 days. 12 lunar months is 11 days too short, 13 lunar months is 19 days too long. And so if you stay with that, pretty soon your lunar calendar is going to get out of touch with the seasons. And this is the whole battle of keeping the time that the sun says it is versus your imposed man-made calendar on it. And so if you don't keep them aligned, well, if you wait long enough, then the hottest time of the year is eventually going to occur during the winter months. And so your calendars have drifted to the point where you've got opposite seasons. So many cultures got around this conflict of using the moon, the month, by inserting an extra 13 months every few years in order to synchronize their seasonal and calendars. Okay, their seasonal solar calendar and their man-made calendar together. Okay. So out of this comes something about the moon. So it was kind of accepted practice in Babylon about 4,000 years ago that for about a month after a wedding, the bride's father would supply his son-in-law with all the mead he could drink. And mead is a honey beer. And since the calendar was lunar-based, this period of time after the wedding was known as the honey month because you could drink all the honey beer you wanted. And this is the origin of the word honeymoon. This is where this comes from. I'm not sure any bride's father today would give his new son-in-law a month's worth of free beer. But that's where it comes from. And there's several other terms associated with using the moon as a time marker within a year. It's where we get the terms lunatic, luna, blue moon, wet moon, harvest moon, lots of moons marking various time points within a year. Okay. So this went on for a while, and it was the Egyptians who gave up on using the moon to mark time within a year, and they took a more radical approach in trying to keep the seasonal and the calendar years synchronized. It is they who gave us, or inherited, but implemented it. They divided the year into 12 months of 30 days each, period, for a total of 360 days. 360 days, easily divisible by 12. It's also why there are 360 degrees in a circle. This is where this comes from. It's why there's not 5 degrees in a circle or 1,000 degrees in a circle. A circle is 360 degrees. We define it to be that because it takes about 360 days for the Earth to go around the sun. And so at the end of every year, they added 5 days for an approximation of 365 days. Now, even the Egyptians knew that that was too coarse of an approximation to keep the seasonal and calendar year synchronized. And so they inserted extra days at random. Whenever it got too out of whack, they would just insert an extra day to keep the seasonal and calendars years synchronized. So this went on for a while, and then the Romans came into the picture. And originally, the Romans had a surprisingly messy calendar. Their year was 10 months long, and March was the first month of the calendar. And extra days were inserted at random all across the Roman Empire at different times to keep their local seasonal and calendar years together. And some of the remnants of the Roman calendar are still with us today. September, October, November, December are from being the 7th, 8th, 9th, and 10th months of the Roman calendar. If you speak like Spanish or you speak any language of that, you'll instantly recognize as you count to 10 Uno, dos, tres, cuatro, cinco, seis, siete, ocho, nueve, diez. 7, 8, 9, 10. That comes from the Romans. Of course, we don't use them as the 7th, 8th, 9th, 10th, but that's where they come from being the original Roman calendar. So this was a nutty system over a large enough empire. And so 1 year before his death, it was Julius Caesar who instituted a new calendar. There's going to be 12 equal months. March is still going to be the first month of the year, 365 days. But now I'm going to organize when those extra days are inserted, not at random. We're going to do it every 4th year or leap year. We're going to add 1 extra day at the end of the year. And so he basically organizes when that day is added. And this gave an average year of 365.25 days. And remember, the real seasonal is 365.2422. So that's a pretty good approximation, 365.25. And Julius liked his new calendar so much that he decided to name a month after himself. This is where we get July. July is named after Julius Caesar. And like a lot of things, politics and money kind of go together at some point. And so Julius had a very wealthy benefactor, speaking of billionaires, Bill, who was known as the Juno family, who supported Julius with their billions. I don't think they had billions, but the equivalent of billions in the time. And so he honored them as well by naming a month after them. This is where we get the word June. So that's from the Juno family from the Romans. So you can start seeing a lot of our months actually have a Roman heritage to it. Well, now the pattern's set. All right, so Julius dies, and now every Roman emperor after Julius has to honor himself by naming a month for himself. Fortunately, this didn't stick. There's only one that stuck, and that was Julius's grandson, Augustus Caesar. And it's where we get the term August. August for Augustus Caesar. So June, July, August, the summer months are all from the Romans circa Julius and Augustus Caesar. So 365.25 is pretty good. It's about 11 minutes too long, or about 1 day in 130 years if you don't do anything, or about a week after 1,000 years if you don't do anything. And naturally, nothing was done. So after 1,000 years, it gets kind of nutty. Your seasonal and calendar years are clearly becoming out of sync. It's noticeable. And so by now, the Catholic Church is in power. Rome is in power. And so by 1582, we were about 10 days out of sync. And so Pope Gregory decided this was nuts. We need to resync our seasonal calendars with the calendars we like, our man-made calendars. And he introduces what is called the Gregorian calendar. So I want you to look at that October 1582 calendar and notice something. October 1, 2, 3, 4, 15. So the first thing he does is just lop off 10 days right out of the calendar to get the 0 point back. And of course, this causes near social chaos, right? What if your birthday was October 5th? Does that mean you don't have a birthday? If I'm an employer, do I have to pay people for their week's worth of work they didn't do? All kinds of social chaos. Anyway, they figured it all out in the end. It was all good. The calendar went on. So now we've reset the 0 point. And this is where, from Pope Gregory, that now January 1 becomes the beginning of the year, right? So we're going to get rid of the pagan Romans March and move it over to January. So this is where January 1 comes in. Every 4 years, an extra day is added, not at the end, but now at February. Okay, so far he hasn't done anything. That's just Julius's system right there. He just shifted when the days are added, shifted the 0 point. So he hasn't really done anything. But now he makes a new addition, a new correction, and decides that century years that are divisible by 400 are also leap years. So 1700, 1800, 1900, these are century years, but they're not evenly divisible by 400. And so therefore they are not leap years. But the years 1600 and 2000, Y2K, we just went through Y2K, those are leap years because those are easily divisible by integer numbers divisible by 400. And so this is the Gregorian calendar that comes in. And this Gregorian system is a better approximation. It's only 38 seconds short. too short of the seasonal year. Or if you wait long enough, it's about 1 day in 2,200 years. And we've been on this train. Are we going to do it again? Are we going to wait another 2,200 years, 10,000 years before things are seriously out of whack again and we have to come up with a new 0 point, yet another correction? No, we don't do that anymore. So what we do now is 1 second, instead of saying is added, I should say can be added to the calendar clock at midnight on June 30th or December 1st. So it can be added. It doesn't have to be. But when that difference between the seasonal year and the calendar year gets out of whack by 1 second, we say that's enough, and we're going to make an adjustment. And so the calendar clock, that's our clock. That's the time we want. Our imposed time order on the universe is maintained by a system of atomic clocks maintained there in France with the Bureau International to maintain the calendar clock based on atomic clocks. The seasonal clock is actually based, of course, on Earth's rotation, right? That's what spins it around, as Earth spins. And that is done by by the U.S. Naval Observatory at the International Earth Rotation Service, which is shown in that image on the right. That's just a lovely looking brick cinder block barred window. What's going on there is so important. They're measuring the rotation of the Earth. Ooh. Very important. You need that kind of building. So it's those two that we keep in sync: the calendar clock from atomic clocks and the seasonal clock by monitoring the Earth's rotation. And when those two get out of sync by a year, we can, twice a year, bring them back into alignment. So that's time in months and years. How about weeks? Where do weeks come from? How come we got 7 days in a week? We got 7 days in a week because to antiquity, there were only 7 objects that moved on the night sky. So they have to be pretty special. Everything else just stayed there, sticky dots on the celestial sphere. So only 7 of them moved. And those 7 objects are what we call the planets and the sun. So sun, Moon, Mercury, Venus, Mars, Jupiter, and Saturn. And so there are 7 days of the week because there were 7 objects that were known to change on the celestial sphere. And so our names for the 7 days of the week come from the North Celtics. We have the obvious Sunday. Then we have Moon Day. And then we have Tew, North Celtic for Mars, Tuesday. Woden Day, Wednesday for Mercury Day. We have Thor Day. Probably everybody at this point knows about Thor. All right, so Thor is Jupiter. That's Thursday. And then we have the lone female. We have Freya, Venus, Friday. Freya Day, Friday is Venus's female day. And then we have Saturday, or Saturday as we call it. And that's where we get the 7 days of the week. Okay, so lots of astronomy in our directional, cardinal directions and our timekeeping. Because that's the origin of how we kept time. How about time zones? Where did those come from, right? Who implemented that? Well, again, that's a man-made device. And before the railroads, time zones were set according to your local astronomy conditions, completely appropriately, because that's what's accurate with your local conditions. But once you start getting large-scale transportation systems, in particular the railroads, in the 1800s, that becomes a bit of a bear. When you say when a train is going to arrive or depart, are you talking about when it leaves New York? Are you talking about the local time? What a mess. You can't even create schedules because every place has its own local conditions. So it was the trains, transportation systems, that established the time zones in the US. And those worked well, so well that Congress made it federal law in 1918 to have these 4 time zones across the US. And then shortly after that, the forerunner of the United Nations implemented it worldwide. Of course, airplane travel is coming in vogue at this point. And so that's the origin of the 24 time zones across the US is basically transportation systems. And of course, as you look at this map, you can see that those 24 time zones, how shall I say, they bow to geopolitical pressures. They're not straight. They go around things. They obey human whim on where to cut the lines, and that's all perfectly fine. But the time zones come from transportation systems. That's where I got that. And I think that's all I wanted to say about clocks and time and how we got where we are on clocks and time. All right. And
thanks, Frank.
Sure. I went a little long. Okay, I'm back. So yeah, I went a little long, 5 minutes, so we should wrap it up here. Okay, thank you. Bill and I will be back in 4 weeks, 5 weeks. And we'll do another session. It'll be 12 hours different. So instead of starting at 0500 UTC, we'll start at 1700 UTC. So we can try and get the other half of the globe. And we'll go from there.
All right.
So thank you everyone for tuning in, listening, watching, live or recorded. Don't forget to ask your questions. On the discussion board, you've got ID verification coming up. If you want this course for college credit, I think that due date is tomorrow. I have to check, but it's coming up very soon. As is your first quiz. Your first quiz is due here on this coming Monday. So ask your questions.
All right. Thanks everyone for the questions, and we'll talk to you soon.